So welcome everybody. Today we have the second lecture for the web analysis. In this lecture, we are going to have two sections where the speakers will focus in two different use cases. And then after these two sections, you are going to have the opportunity to ask questions. For that, you have two options. Write the question in the chat, and then I will read it, and then they will reply. Or you can raise your hand with the reactions thing in Zoom, and I will give you the turn, so then you can ask your question. Okay? So thank you very much for joining, and the floor is yours.
Thank you, Maria. Let's see if I can share my screen. Do you see my slides?
Yes, perfect.
Okay. So welcome everyone, and thank you for joining in this second lecture of the SWAN academic training. Perhaps I can start with a bit of a summary of what we saw yesterday in the first lecture. So yesterday we saw mainly an overview of the service. We saw how you can create your session in SWAN, what are the parameters that you can choose, like the software release that you want to use. So in SWAN, we based our software environment in these LCG releases where you have all these packages, hundreds of packages available for you that you can use from your notebook. We also saw that when you log into SWAN, you start your session. CERN box is your home. So you find there all the user files in your storage space, and you can access them from the notebook. You can also create projects in your CERN box that contain notebooks and share it with others. And these other people, they can see what these projects contain and eventually clone those projects into their own CERN box. And then we also saw that from SWAN, you can actually access other resources, external resources, like we saw the connection to Spark clusters, so you can offload computations to Spark clusters. We also saw that you can attach a GPU to your SWAN session. So this is also possible in SWAN. And in the end, so at the end of the lecture of yesterday, we started talking about use cases. So what we know that people are using SWAN for, and today we're going to focus on two of them, and we are going to explain them in a little bit more detail. So I'm going to start with that, with the first use case that we selected, which is physics analysis. So I already introduced this yesterday. SWAN can be used for doing interactive physics analysis. It's usually not a big analysis. It's rather medium, small size. This means that the input data is maybe some gigabytes, and it's simpler format like nano-ODs or n-tuples. We will see an example with nano-ODs today. The input data, you can have it on your CERN box, or you can have it on other places on EOS. For instance, you have project spaces, so you can share some project with some other users. Or you can also access data with your credentials, data that is on some experiment repository on EOS, right? EOS CMS, EOS Atlas, etc. And then so for software, you have the LCG releases. So these 500 packages that include things like root, the Python data science ecosystem. Actually, we're going to see now in the examples both root and data science libraries like NumPy and pandas. And yeah, so you have plenty of options there. So now moving to the concrete example that we're going to see today. We're going to see this analysis is a dimuon spectrum analysis done in SWAN. The input data is CMS open data that is located on EOS, actually on EOS public. And we are going to analyze it. We're going to use a few tools. So the first one is root, and in particular RDataFrame. I will give more details about that in a minute. And what we're also going to see in Python, how to use NumPy, pandas, and matplotlib a little bit from the notebook. We are actually going to see two flavors of this. We're going to see the same analysis in C++ and then in Python as well. And we're going to see how to create these interactive plots in a notebook. So before I go to the training material, I have the link there. Let me just do a brief introduction about RDataFrame. So Roots RDataFrame is a tool that helps you process data sets that are on this columnar format. We're talking about columnar data here that looks like this. So you have your data set that contains a set of entries or events or rows. And then each of these entries, they have some properties, columns or branches in the root jargon. And these columns, they can be of basic types, they can be arrays, or in general, when talking about the root format, they can contain any kind of C++ object, actually. So RDataFrame processes data sets like this. And it does it by applying, normally you apply as a user the same series of steps. Perhaps you're already familiar with these steps if you have used other data frames like Spark data frame or Pandas data frame. Some of the concepts are similar. But with RDataFrame, what you do is you build first the RDataFrame from some data set. Then you apply some transformations to your data set. You can, for instance, apply some cuts, filter events, or you can define new columns, maybe starting from some existing columns in the data set. And then in the end, you want to get some results. So what you do to obtain that, you apply actions to the transformed data, and then you get results, for instance, a histogram. Right? So these three steps are illustrated in this slide. So very simple, creating the RDataFrame first, in this case, reading a root file and a data set that is stored in it. It's a T-tree. And then what we do is we first transform this data set. We apply a filter. We only want the events for which theta is greater than 0. Okay. And after that, we want to create a histogram of one of the columns of the data set, in this case, PT. And that's our result right here, the histogram that then maybe we can draw. So in the end, what happens under the hood is that RDataFrame creates this computation graph that starts from your initial data set, and then for every new operation that you add, a new node is added to the graph. Right? So you create here a filter, then a define, and then here you can maybe branch out and do 2 histograms, one for a different column. And only when you actually access one of the results, like one of these histograms in this case, the actual computation will happen. So the event loop will be triggered lazily when you access a result. So yeah, that's everything I wanted to say about RDataFrame. So I'm going back now here because I want to go to the notebooks already. So yeah, so I'm going actually to change this because I want to start fresh my session. I already had a session for that. Let me try again. Yes, so first I'm going to create my session with the material that I want to show. I'm going to select here these cloud containers. You'll see later why, because one of the notebooks will offload computations to a Spark cluster. So I will just select that here and I will explain later. So what SWAN is doing now is it's starting my session. And I clicked on that link that is referring to a repo that contains some of the notebooks that I want to show now. It says it's downloading those notebooks into my CERN box. So when that is done, I will be able to show you the content of this training. You will see that I have a few notebooks. Yeah, so this is done. This is some repository on GitHub that we prepared, and now I opened it in SWAN, and this contains the content that I want to show. So I'm just navigating a little bit. I'm going to this folder, and here I have some notebooks. So I have 3 of them. They all contain the same analysis. One of them is written in C++, then another one in Python, same analysis. And then there's a second Python one which will run the computations distributedly with Spark, but I will show you that at the end. So let me start with the C++ one, which is the first one. So this is the notebook. So this is a C++ notebook. In SWAN, you can create or you can write C++ from the Jupyter interface, thanks to this root C++ kernel. So before I go into details of the analysis, I'll just show what you can do in a C++ notebook. So what you type here is C++, right? So what you type in the cell, C++ code. And this is possible because root has this C++ interpreter that will take what you type in the cell. It will just-in-time compile it and run it for you. So this is what just happened when I run this cell. And then I wanted to mention a feature that is very neat, I think, which is this shadowing feature. So when I started doing trainings with C++ notebooks in SWAN, one problem that we had is that often people got frustrated because they had cells with definitions, variable definitions, and it's very common when you are in the notebook that you rerun cells multiple times. And because of this one definition rule of C++, those people, they were getting an error when they run it the second time because they were redefining stuff. And that was a problem, I think, for the usability of C++ notebooks. But now root provides the shadowing feature that allows you to define a variable once. I just ran that cell, now I'm running it again, and I can run it as many times as I want. And each time the previous definition will be shadowed. And you can even change the type of the variable, right? So I can make it a float here, right? You can see here that this is a float now. And so this is particularly useful, I would say. I wanted to mention it because when you use C++ from a notebook, this can be something to know, that it's good to know about. Right, so this was it for C++ in a notebook. Now let's talk about the analysis itself. So it's the immune spectrum analysis. So the material is taken from, so these notebooks are based on some work done by Stefan Bunch, which is available here in this link in the CERN Open Data Portal. So for any physics related questions about this analysis, please refer to that. But what we are going to do basically in this analysis is first we're going to create a root RDataFrame, and we're going to connect it to a data set that contains 61 million events. It's open data recorded by CMS in 2012. Then we are going to transform our data set. We are going to filter the events relevant for the analysis. By the way, if you need this to be bigger, please let me know. If this is fine, I think this is fine. Otherwise, I can make the font bigger. Right, so we filter the events, then we are going to add new columns to the data set. We're going to compute this invariant mass of our immune candidates. And then we're going to plot the invariant mass. This is what we're going to do here. So the data set looks like this. It's this nano-LD format. It's basically, you see here, there's a column that is an unsigned int, and then the rest are arrays, right? So rather simple. And the first thing that we do is we are going to create our data frame out of this data set. Here I want to point out, you see that the data set is on EOS public. It could be also on my CERN box, right? I could be taking this from my CERN box, or it could be on some EOS project, or it could be, if I were an Atlas user, it could be in the Atlas EOS repository, and then I would access it with my credentials. But for this demonstration, it's on EOS public. Now, so with DataFrame, well, you have some operations to inspect the data set. You can get the names of the columns of this data set. You see here this list. You can get the type for a particular column. Like for this one is an unsigned int. Then you have this display operation that you can run to see how the data set looks like. You see that we have all these columns, and then these, for instance, this is one entry of the data set. This is another entry, right? You see how the first entry has 2 muons, and then we have some properties for those muons. So this is how it looks like. Then here we're only going to run on part of this data set. So this data set, like I said, it's 61 million events. You will see here in this result. I'm going to run on only 1 million for the sake of time, because we don't have that much time. So I took, with this range operation, I took only 1 million events from this data set. And now I'm going to start transforming the data set. I'm going to apply a couple of filters. So the first filter is going to select the events that have 2 muons. And the second filter is going to select from those previous events, the ones that have, for the 2 muons, they have opposite charge. So if we look at the data set, for instance, this first event has 2 muons, but when we look at the charge, it's not opposite. So this one would not pass the second filter. It would pass only the first filter. But then the second event has 2 muons. It would pass the first filter. And then they have opposite charge. So it would pass the second filter as well and be relevant for our analysis. So I'm going to run these filters. Like I said previously, this is now just adding nodes to the computation graph of our data frame, right? So these filters, they didn't run any computation yet. But you do run some computation if you want to have a report on how your cuts are doing, how many events passed these filters. Here you have that information, right? So from 1 million, this many passed, and then from the ones that passed the first filter, how many passed the second filter, right? So you can get that information. Right. So we applied some filters. Now we're going to define a new column. And we're going to define a new column, which is the dimuon mass. Is the invariant mass of these muon pairs that we just filtered. And we're going to do it with this define action, where the first parameter is saying, so this is the name of the new column. And then this is a C++ function that is going to be applied to all these columns for every event. So this is basically saying, create a new column in my data set that is going to apply this function to these other columns for every event. And this is what we do. Once we have that column defined, we can actually create a histogram out of it, right? So this is what we do in this histo1d call. Now we want to create a histogram for that column. And now we get to the point where we actually run. Why? Because you see here this histogram that we got out of this histo1d action. Now here we are accessing it for the first time, and now the event loop run in C++. And it took this almost 4 seconds. And now, since we already have the histogram, we can plot it, and here you see the result. This is actually interactive, right? So you can zoom in if you want. Yeah. And this concludes the example of the analysis for C++. Let me check how well are we doing on time. Okay, so I'll hurry up a little bit because I want to show it also in Python, and if I can, distributedly. So now this is the same analysis in Python. You can also do Python from SWAN, right? So we are going to run the same analysis. I'm not going to go into detail of everything because we just saw it in the C++. So this is the same, but in Python. In Python, you can also run root because root provides these Python bindings, which are called pyroot. So you import the root module, and then you have all the functionality that you have available in C++. You also have it available in Python, including RDataFrame. But under the hood, and this is important, under the hood, everything runs in C++, because those classes, they are implemented in C++. So Python is just the interface language. So all the heavy lifting happens in C++. The event loop happens in C++. So again, we create the RDataFrame from the CMS dataset on EOS public. It's the same. We can inspect it. The same thing we did from C++. Display the dataset to see how it looks like. And then again, we can run on just one part of the dataset. So we apply again one range for 1 million events. Now we do the filters. Here it's important to know that these are actually C++ expressions, even if you are running from Python. So under the hood, this will be wrapped by a C++ function, and it will be just in time compiled for you and run. So yeah, so everything actually under the hood happens in C++. Again, we can create a report of the cuts. This is the same as in C++. We can define a new column, the invariant mass for these dimuons that we selected. The histogram, again, it's the same thing. And now we get to the cell where everything runs, because we access the histogram for the first time. And yeah, so you see how the time it took to run, it was very similar to the one of C++. And again, this is because actually almost nothing happens in Python. Most of the heavy lifting is done in C++. The event loop happens in C++. So it's normal that the times are similar. And now again, we have this dimuon mass plot, and you can see how it's actually the same one that we obtained here. Now we obtained it from Python. But we are in Python. We are going to do something more in Python. We're going to use other tools because we have the Python data science ecosystem, and these packages, they are provided in SWAN as well. So we are going to run this as_numpy function of RDataFrame, which is going to transform one of the columns of this data set, the dimuon mass column, into a NumPy array. Actually, we'll return a dictionary, a Python dictionary with just one key, and that key points to a NumPy array, which has the contents of that column. So once we have that, we can, for instance, go and use pandas. We can create a pandas data frame and work with it and inspect it, right? Because this is also available in SWAN. Or we can go to Matplotlib. We can do the plot of the dimuon mass in Matplotlib as well from our notebook, and this is also interactive, right? So yeah, the take here is that you can use in SWAN, you can pick one tool to do your analysis, or you can even combine different tools in the same notebook as we did here. Right. So okay, so I only have a few minutes left. Let me see if I can go back here and I can run the last notebook. Again, this notebook is it's a Python notebook, but it's a bit different from the previous one. So here we're going to run exactly the same analysis again, but this time we're going to offload computations to a Spark cluster instead of running everything in my SWAN session, let's say locally in my container. So what we're going to do here, again, we're going to import root, the same as before, but we're going to use this library called PyRDF, which is a Python library that is implemented on top of root. And what it allows is for RDF computations, RDataFrame computations, you can select more than one backend. So you can run the computations locally, as we did in the previous notebooks, or you can also run them. In this case, we're going to run with Spark. Yesterday, there was a lot of interest in Dask. So actually, it was already discussed to implement a Dask backend for RDataFrame. So that could exist too. But here today, we're going to use the Spark backend. And we're going to say, yeah, we want to use the Spark backend, and we're going to partition our data set in 16 fragments. This will allow us to create the parallelism. But before I run this code, what I want to do is I want to connect to my Spark cluster. So I clicked on that button, and here I already had 2 parameters configured. Since I have 16 partitions, I want 16 cores. So I'm asking for 4 Spark executors with 4 cores each. And that's what I'm requesting here. And now it's creating this Kubernetes Spark cluster for me with the 4 executors with 4 cores each, 16 cores, because in the end, we want to offload computations to that cluster. So now it's done. I can go to the notebook and I can start running my notebook. So I'm going to do that. Here you see how the analysis from this point, it doesn't change. So it's the same steps we followed in the previous Python notebook, when we were running locally. There's one difference though, that we are not going to do a range. This time we're going to run on the entire data set, the 61 million events, because we have more resources. We're going to run on the 16 cores, right? So now instead of 1 million, we will just run on the entire data set. And all the steps are the same. I will not repeat myself, the filter, the define, creating the histogram, right? All of that is the same. And then we get to our cell where we actually run stuff. And this time what happens is that there's this Spark monitoring display appearing where you can actually see how your job is doing. So this is being offloaded to the Spark cluster, the RDataFrame computations. So hopefully we can see here some of the tasks that are running, and yeah, and this is now running in the Spark cluster. And in the end, when this is done, I can just draw the plot again, and this time it will contain more statistics because I run on the entire data set, right? But it should be all, basically the same result. Okay, so here I see the tasks are running. So I'll just leave this running, and maybe since we are running short of time on my section, I can already start getting some questions. So yeah.
Okay, I can see the first question from Stefcho. I didn't get the nice Spark progress bar. Am I missing something?
You didn't get it because you need to have, first you need to create your session. If you remember, when I created my session, I selected the Kubernetes cluster. There's in the web form at the beginning when you create your SWAN session. I can show you actually, maybe easier.
Yep, I did exactly that.
Yeah, and then you need to connect, as I did, to the cluster.
Yep.
But you have also access to those clusters. Have you been granted with access? Because I think you need to be granted with access before you use it.
Okay, that might be the explanation then. Okay,
yeah,
thanks.
So for this, yeah, please write a message to us, send that, or post on the SWAN community, or if you want to open a Snow ticket as you wish, and we can give you access.
Good. I cannot see more questions in the chat. Neither raise hands.
You still have some time. I will just show, because now it finished. I will just show how you see here, if we compare this plot with the equivalent, here we were running only 1 million events. In the other one, we run on more. We run on 61 million. So the shape is a bit different, but it's because we are running on more events. We have more statistics. That's everything I wanted to say. So maybe if you have more questions at the end, I can also answer. So I'll just unshare and then give the floor to Prasanth so that he can start with his use case.
Thank you, Enric. So good morning, everyone. I'm Prasanth Kothuri. Let me share the screen in the meantime. Can anyone confirm if they can see my screen?
Maybe if you can put it full screen.
Yeah, you need to make it full screen.
Yes.
Okay, so that's what it was, but let me share again.
Now, perfect.
Okay. So second time works. I will go through the introduction to Apache Spark and how you can exploit Spark on SWAN with two use cases. One is on the data center operations, and the second one is on BE department NxCalls project. NxCalls is a new logging system that's based on industry big data technologies On the back end, you have HDFS file system and H-based database that stores the data. On the front end, you have Apache Spark together with notebooks or some other way to extract and analyze the data from this NxCalls system. Like I said yesterday, Spark is a unified compute engine that can do parallel processing of your data. Apache Spark is an open source community effort, and the community has this philosophy. So it is a unified platform for writing big data applications. So that means it can do several things. So it can do a typical ETL, it can do a string computation, it can also do graph computation. Why this is important? This is important because in the early days of industry big data technologies, we had several tools for each of these use cases. So we had like something like Scoop and Flume for loading. We had like Hive and Presto for SQL. Whereas the Spark community decided to have a compute platform that unifies all these use cases. And also Spark limits itself to computing. So it doesn't care that much about the backend storage systems. So it can load data from several persistent storage systems, like for what concerns us in SWAN and our organization, which is HDFS, and experimental data from EOS, which Enric has shown. And it can also load data from S3, which is one of the services that IT provides. We have a wide variety of libraries in Spark in addition to the core packages. So we have packages that can load several types of data formats. So if you take a text format like CSV or JSON, or if you take a binary format like Parquet, which is also optimized for data analysis, or even some of the data formats that we use in research, like these hierarchical data formats like HD5. A Spark application primarily has two things. So one is a driver process and another one is a set of executor processes. A driver process is what that lives on the SWAN notebook, the Jupyter notebook that you have seen in the last 2 days. And the executors are the processes that are spun up on the compute clusters external to the SWAN application. So driver process is all about coordinating and scheduling the work to the executors and also responding to the user input and also showing you the aggregated view of the data or a little bit more data that you can save to the persistent storage. Executor process is what that does the computation. So it does the heavy lifting of applying your functions on the data. And in the end, it can return the state back and also some form of aggregated view of data to the driver. Or it can store the data back to the persistent storage systems. What is important here is when you want to collect data into the driver process, you have to take in account that driver process has a certain amount of memory, and if you collect data beyond what you can fit in this memory, typically you can get out of memory errors. So the good practice is only collect the data in the driver process aggregated view of your computation. This is how the picture looks like. So for what concerns us, on the left side is the driver process that lives in the SWAN notebook. On the right side are the executors that can live in any of the clusters that you can access from SWAN. And since Spark is a distributed computing framework, so you always need a cluster manager that can make these heterogeneous resources as one entity. In SWAN, we use two cluster managers. So one is Yarn and one is Kubernetes. Okay, so how do you process data in Spark? So Spark has APIs. So there are two types of APIs. So one is unstructured API that can process text files or any unstructured kind of data. So which was like early developed and used in the early days. But nowadays we have much more optimized higher level structured APIs that can process structured data, be it text structured like JSON or binary structured like Parquet or some other format. In this talk, we only focus on high-level structured APIs, and this is called data frame. So this term is not new. So this is already known in R as a data frame, and also popularized by the Pandas package as Pandas data frame. So essentially, data frame is, you can imagine as a table with rows and columns. So the header of the data frame is what is called schema. So it has the names as well as the types. So be it your string or a data. So you can think a data frame as a spreadsheet, even in a simpler form. The important thing is a spreadsheet can live only on a single machine, whereas a Spark data frame can span across a huge number of machines. What gives parallelism to Spark is partitions. So to allow each executor to perform computations in parallel, you have to break up your input data set into partitions. So there are several ways to do it. So if you use a, let's say, big data native file system like HDFS, the partition happens implicitly, so you do not have to do anything. So a file is already chunked up into what are called blocks on a HDFS file system. And I have some chat. Okay, so we take that in the end. So if you use a Hadoop native file system like HDFS, your data is already implicitly partitioned, and you don't have to worry that much. And the more partitions you have, the more parallelism that you can get. So if you only have one partition, but you have a lot of cores to work with it, you're simply wasting resources. And at the same time, if you have too many partitions, but you can only acquire a few cores or a few executors, so you could as well use Python on a single machine. So Spark doesn't really help you here. So this is an example that can give you a better idea of how the data frame and the partition works, and also the attributes of a data frame. So here I take a range of numbers and convert into a data frame. So the range from 1 to 25. So here I have not specified the number of partitions. However, you can, as a second parameter, you can specify the number of partitions that you want for this data frame. And assuming you have 3 workers, so you could have a few partitions on each of this worker. So what is important when it comes to Spark data frames is these properties. So as I said, partitioning is important. And the next thing is Spark data frames are immutable. So that means you cannot update or delete records in the data frame. So you might think, then what is the use? However, you can apply what are called transformations on this data frame and obtain another new data frame. That's how the whole processing works. And Spark is a memory-first computing framework. So it can cache as much as data depending on the availability of memory. And also data frames follow what is called lazy evolution. So when you apply a function on it, nothing happens until you do an action. We will see what are the actions in the next slides. So there are 2 things you can do on a data frame, so which is quite simple, right? So if you have less things, you have less things to worry about. So the first one is transformations. So these are basically the functions that you can apply on a data frame and return another data frame. So the second set of operations are actions that actually trigger the computation. So the actions can be collecting the data or saving it back to the persistent system or visualizing with any of the plotting frameworks, for example, in Python. Okay, so 1 second. Okay, so we have transformations, as I said. So this is instructing Spark on how you would like to modify data frame or call transformations. So essentially, this is a small example here. You apply a function on a data frame, you get another data frame. So this is how you express your core logic using Spark, and these are lazy. And there are 2 types of transformations. This is important, but I will just briefly explain, not going into too much detail. So these are called narrow transformations and wide transformations. Why this is important? So as I said, Spark works with a distributed set of data across several machines. So in a narrow transformation, the result is only dependent on one input partition. So that means you don't have to move data between machines. A simple example is what you see above. In a wide partition, the result is dependent on multiple input partitions, so which could reside on two different physical machines, which trigger what is called, transfer of data or shuffling. So an example could be order by or a group by operations. Typically, they say you have to avoid wide transformations, but you probably have to use it at some point. But you just have to know that these are time-consuming operations, and the Spark community is always working on optimizing this in terms of compression and caching. Okay, so the action is what triggers the computation. So you start with the input data set, you apply a bunch of transformations and an action. So Spark builds what is called a direct acyclic graph and then executes this graph. So there can be multiple types of actions. So some examples is you want to view the data in the notebook, or you want to collect the data into respective languages. So for example, you can also convert a Spark data frame to Pandas data frame. So this is called an action because you are getting this data into a native language object, which is your Pandas data frame. Or you can write back to the storage systems, for example, which is typically the case in terms of ETLs. Okay, so now I will show you a couple of examples. So the first one is on the data center operation. So how all these things fall into place. And the second one is on the NxCalls. So let me share my Google Chrome. Okay. So I hope you see my screen. So I'm logging into SWAN here.
Yes, I can see it.
Okay, thank you. Okay, so here you have the software stack. So in this case, you can choose the latest one. So Enric has already explained the cloud containers cluster. So here I'm choosing the cluster that is analytics. So because this is where the data center information is. And I say start my session. So some setup work is done here. Okay, so in the slides, you can access these notebooks in SWAN gallery, like we showed yesterday. So we collect examples for several use cases and make it available for users, which is a good way for you to get started. So these notebooks, how you can access is already in the slides. So in my case, I have this in this academic training folder. So the first one I would like to go through is analytics host metrics final. So I open the notebook. So I will also, like we said yesterday, within the notebook, we give you certain tools to make the data analysis a little bit easier. So the first one is if you click on this elephant, you can browse the HDFS file system. So this can be useful sometimes if you don't know where the data is and if you have to search it out. And the second one is the star button that allows you to make the Spark session. So when I click on it, in this case, I do not need any additional configuration. So for most of the use cases, the default configuration is already enough. So unless you are a power user, we do not recommend you adding any additional configuration. So when you connect, this is when a connection is established. So even though we are using the Python API of Spark, Spark itself is written in Scala and runs on JVMs. So what is now happening is it is trying to instantiate these JVMs on the external cluster. Usually this takes up to 15 to 20 seconds. Okay, so once you have this connection, we also provide you some details. What is the version of Spark you are using? So typically, unless you had some old applications, the latest one is always good. So we already do quite a bit of testing and ensure that the latest stable one comes to the SWAN. And you can also see, as I said, one of the actor that lives on this notebook is called a driver. So you can also see the logs of this here. Okay, so now let me go to the notebook. So this is an example that shows how you can access external compute resources and profit from having lots of cores. So I just try to import some stuff I need. We return, once you do the Spark connection, we return a Spark object back to this notebook, so which you can see here. So it just shows you the session and the name, which if you want, you can change, and the cluster manager, which here in this case is YAR. Okay, so we have a project in IT, it's called IT monitoring. So they nicely collect the data from all the physical machines and then store it in this path. So the root path for their application is project monitoring collecting. So what I am trying to do in this example is trying to visualize the load on one of the services that we run, which is NxCalls. So the load metrics for these machines are available in what is called a load folder, and nicely you have folders with year, month, and day. So I'm trying to load the load data of my service for 14th of January 2021. So this comes back quickly because the actual loading has not happened. So what Spark does is it will see how many files it has, how many partitions it can convert into, and it tries to infer a schema. So what we had there, I think, is a compressed JSON, which we were Parquet actually, sorry. So you see the spark.read.parquet. So these are the Parquet files, which are binary row optimized files. And you can, if you are a beginner, so first you can try to figure out what is the structure of this data and the data types. So here I have what is called a submitter host group that tells me what is which service I'm interested in, and also the value. So that is the value of this particular key, that is load. For this data frame, so I'm not actually trying to use data frame. So let's say in my case, I'm a little bit more familiar with SQL. So you create what is called a table alias for this data frame, like this in Spark. So df.create or replace temporary view will create an alias view that's called load average that essentially points to this data frame. So when I have this, I can try to access this load average with a SQL statement. So here, if you go here, we will come to the columns later. So you see, I'm trying to select from this table, which I just table alias, which I just created. So from this table, I am selecting the data because these folders here have data for all the services. So I'm doing filtering of only the service that I'm interested, and that's called Hadoop ng NxCalls prod for the day of the month, which is 14. And I'm also grouping by hour because I want to visualize this by hour by host. And I'm computing the average value. And this is what actually is sent to the Spark executors. So okay, whatever I said here, heavy lifting is done in Spark, and the result comes back as a Spark data frame. But since I want to use some Python plotting libraries, the result of the Spark data frame, I am converting into a Pandas data frame. So the execution of this statement actually returns a pandas data frame. Okay, so now I have this Spark monitor, another utility we discussed yesterday, and also you have seen in the previous examples. So I have gone with default configuration. So the default configuration is very good because if you don't need external compute resources, you don't have any. If you need, they are started up to the quota that you are allowed on this particular cluster. So here I started with 2, but Spark said you have a lot more partitions. I can go and take up to 64 cores. So this is typical user quota we have on the cluster side. So I had 32 executors, each with 2 cores. So I managed to use 64 cores for 34 seconds to process a lot of data. So in data center, we have lots of machines, and these are collected at regular intervals. I don't know, 10 seconds, 20 seconds. So we basically processed quite a bit of data in 34 seconds using 64 cores. Okay, so now I have this pandas data frame, so you can do several things. I am using a plotting library that's called Seaborn. Seaborn is actually based on matplotlib with a wrapper with a better CSS. So here, what I have is a host, and I have an average value, and I have an hour. So the index, so which is the y-axis. So essentially, I'm plotting a heat map. So on the y-axis, I have all the machines of the service. Okay, on the x-axis, I have the hour, so 0 to 23, and the average value is plotted as a color map using this color coding. Okay, so you can see that at certain times some servers are busy. So if you have a horizontal line, more or less the server has some issue, and you have to go there and look at it. So if you have dark blue vertical lines, you had either heavy load coming in from the users or from the application guys trying to load more data into the cluster. Okay, so that's one example. So another one to go. Okay, so we still have another 10 minutes. So the another one is, as I said, the IT monitoring team collects a lot of metrics. So we have looked at the load metric. So now we quickly look at the uptime metric. So I would like to see, how the last reboot of the servers in the data center. So I load all the uptimes into my data frame. Okay, I have chosen a date of 14th of January. That's actually last year. So, and then again, I'm creating an alias. Okay, you see. And I'm grouping by host. So again, I'm doing 2 pandas because this notebook shows you the interplay between Spark and pandas and Jupyter notebooks. So here, what happened is we tried to go up to 32 executors with 64 cores. And in the meantime, your notebook has become idle. So you are not using all those cores. So the Spark actually, downscales your resources. And now I have a requirement of more resources, and then it upscales again as necessary. And like we showed yesterday in the slides, so you will see that I have asked for a certain number of cores. And in fact, I'm actually using all the cores that I've asked for, which is good for optimal usage of resources. Okay, so that comes back, and then we visualize I do a histogram again using Seaborn. So what this tells us is most of the so if you see, the Y is a log scale here. So most of the servers have been restarted in the last 1-2 years. However, we have some that have not been restarted since 5-6 years. They are not that many. So this is a log scale. So this is probably a handful of them. Okay, so that's it with this example. You can run it on your own later on to go through in more detail. To run this, you need access to the analytics. So if you already do not have, you send us a ticket and you'll be given quickly. So this is a general purpose to cluster. Okay, so I stop this and I will show. I have five minutes left. I will show the next use case. So that is NxCalls. So as I said, this is a new logging system that a team in Beam's department is developing to store the data from the LHC machine, be it cryogenics, vacuum, many things. And they're storing in the HDFS file system, and they have several interfaces to access this data. One such interface is SWAN. So when you start your SWAN session, we already attach to a particular cluster. So we attach to this cluster that's called analytics. In the case of NxCalls, you have to click on these three dots and change configuration. Since it's a big project and there are a lot of people who want to use it, and there's also requirements of some stable versions, we have a special software stack that's called NxCalls. So you have to choose that, and then a cluster that's be NxCalls is automatically selected. So again, you start your session. So this is okay, so in the academic training, I have this example, that's tutorial NxCalls final. We are the service providers for this project, so we're not actually full experts on their API. So Jupyter Notebooks also provide you a lot of text that you can add in Markdown that explain what you're trying to do. So here I have added the links of this project and the link to their API. So here again, you set up the Spark session and run it. So I will not run this because it's pretty straightforward. So these people have what is called a data extraction API. So basically, you can extract the data that they are collecting from several subsystems. So in their terminology, so you can extract data by device and properties. You can also extract data by what are called variable names, and you can also extract data by what are called key value pairs. And typically you extract this data for a subsystem. So this is CMW or WinCCOA, another example of subsystem, for a duration. So that's a start and end time, and for a single parameter. Or you can also, the API also allows you to have this entity multiple times and extract this for multiple parameters. So once you extract, so the analysis that you do is typically dependent on the experts of BG and in some cases also the TE department. I have some examples of extracting it, and in one case also saving it to my CERN box. Okay, so I will switch back to the slides. Okay, so we have seen these two examples. In case you want to have more information on Spark, so I've also included some references here. For CERN computing accounts, you can also access several of these books from this URL. For any information, further information, you can contact IT Hadoop and Spark service on Spark technology. And for API, we prefer that you directly contact the NxCalls project team. Yeah, that's it. I think we are right on time and we can take a few questions, I guess.
Many thanks, Prasanth. So as I can see here in the chat, there was a discussion regarding the progress bug that was raised by Ben, but I think he fixed it. I don't know if Ben would like to say something about it.
Yeah, sure. I can just report back because I fixed that with a bit of experimentation, and I now understand that the connection to the Spark cluster is tied to the Jupyter kernel. So I was foolishly restarting the Jupyter kernel to clear all my output, not realizing that that broke the connection to the Sparks cluster. So then it was not working until I reopened the connection.
Yes, thank you. That's actually a good point that we should have made. So the life of the connection is tied to the life of the kernel. If you create a connection with the Spark cluster and you restart the kernel, that connection is broken. Restarting the kernel can be useful. For instance, if you connected to the Spark cluster and you requested, I don't know, 10 cores, but then you realize that actually you want to run a bigger computation and you want 20 cores, you restart your kernel and you connect again, requesting more cores, right? So that you can use that for that purpose.
Yeah, if I can add here, this is Steph calling. I also had to change the number of cores and memory in order to get this running. So unlike Ben, I did not restart my kernel. So the problem was not with that, but I had to go into the environment configuration and change it to 4 cores and 16 gigabytes. And then the Spark connection worked. And I remember from past experience that really I was always advised in the past to use 4 cores and at least 10 gigabytes. So that might be the problem.
So you connected to which cluster, the cloud containers or?
This was the Kubernetes, the first example.
Okay, okay.
And for Spark, for the Spark cluster, I just used the default as you advised.
Okay, thank you.
But the NxCall request for access is hanging forever. I don't know if there is the wiki page is not responding there.
So the wiki page that you see in the slides is not responding?
No. When I attempt to use the NxCal clusters, I don't have access to that one yet. And when I try to request access, there is a wiki.cern.ch page which is just hanging forever.
Okay.
It might be a temporary thing, but
yeah, it could be 2 things. It might be a temporary thing, or we have to refresh the link if they have changed it. So we will look into it. Nice. The access is controlled by the NxCalls project team. You can also reach them by the other references that I have put in the slides.
Okay, thanks.
Also, I can see a question from Blachos. Why access to general purpose Spark cluster is not granted by default to all SWAN users?
Yeah, that's that's a valid point. It's not seen as a CERN box or other services where you have access as soon as you have, let's say, a computing account. So we would like to know a little bit more about your use case so that it also helps us to guide you for because in the big data computing world, there are several tools. So we want to ensure that you are using the right tool for the right purpose. In addition, it also allows us to scale, let's say, the resources appropriately based on the user demand that we see.
Okay, thank you very much. I cannot see. Yes, now from Stefan, just arrived one question.
That's all. So you're not blocking resources for more than this for other users. So as you start computation and depending on Spark determines based on partitions how much parallelism it can get, you can go up to 64 cores. So because when we grant access to the cluster, we also create queues that limit the amount of compute and memory that you can use. So the default configuration is pretty good for optimizing the resources that we have on the cluster.
Okay, I don't see more questions. If someone wants to raise any question. If not, I think.
Hey, can I add about the NX cluster and NxCalls access? The request for access doesn't work from the other link either. So the other one points to the CCDE form to generate the email to NxCalls support team, and that one link that link doesn't work either. So there is a problem there. But I'll try later. I hope you'll be fixing that.
Okay, yeah, sure, or chat me directly. So, okay, if I have to open, okay, so since I'm sharing, so I open this link of their API. Okay, so I think they also have, they should have a contact here as well in the FAQ maybe. Yeah, NxCalls access request. So yeah. do you see, okay, so I clicked on the link that we have in the slides.
We see the slides. We don't see the browser.
So, okay, so I have to stop share. Okay, share Google Chrome. Okay. I'm just trying to, okay, so this is the one that the link that we have it in the slides.
Exactly.
So you go to, yeah, so here you see user guide, you expand that, you see NxCalls access request.
Yep.
One thing, I think those links are only visible, if I may add something, those links are only visible from within the CERN network, I think. So if you are trying to access from outside CERN,
I'm outside CERN right now, so
yeah, it could be.
These are under the control of the NxCalls team. It's not under our control.
Okay, so I'll try to proxy then. Thank you.
Yeah.
Okay, so I think finally the question was resolved. So thank you very much. I think it's already the time for lunch. So thank you very much for the speakers. It was a very good presentations. And thanks for all the participants. I hope you enjoy it. So yeah,
thank you, Maria, for the organization, and thank you to the attendees as well. If you have any further questions, in the slides yesterday, we included links on how to contact us, so please feel free to do so.
And also let you know that this is recorded, so then later you will review again the presentations, and even it will be published in YouTube in the academic training channel. Okay, thank you very much.
Thank you, bye-bye.
Thank you, bye.
Thank you.